Hi, I'm Kathy Stark. In this lesson, we're going to analyze polynomial functions of degree greater than 2. We're going to support or do our work analytically and support our work with the graphing calculator, and we'll finish with one application. Let's get started. What we want to do is solve the equation given analytically for all complex solutions, giving exact form in the solution set. Then we'll support our answers, only our real solutions, using a graphing calculator on the given window. The equation we start with is x to the fourth minus 15x squared minus 16 equals 0. This particular one we can solve using the zero product property, which means we need to factor it. With an x to the fourth, we know in our factors we need to have x squared. I need two numbers that multiply to 16 that add to 15. If I use a 1 and a 16, and make the 16 negative and the 1 positive, I've factored, this is a first step, one of these factors, the x squared minus 16, factors further. Let's do that. X squared plus 1, x minus 4, x plus 4. Now applying the zero product property, we set each factor equal to 0 and solve for x. In the first case, to get x by itself, I'm going to subtract 1 from each side. To get x squared is negative 1. Then take the square root of both sides using plus and minus. X is plus or minus the square root of negative 1. Remember that the symbol we use to represent that is the imaginary unit I. In the second case, for the second factor, all I need to do is add 4 to both sides. In the third case, I subtract 4, and I've solved the equation for all its complex solutions. In a solution set, we should write our answers I, negative I, 4, and negative 4. All that we can do on a graphing calculator is support these real solutions, but let's do that much. What we're going to do is graph the equation as y1 and see that it crosses the x-axis, or is 0, at 4 and negative 4. Let's do that. So in our calculator, as y1, we're going to put x to the fourth power minus 15x squared minus 16. It may be that we can get a decent graph on a standard window. Let's try that by zooming 6. If we don't see something we like, we can change the window. Now we don't get the whole graph of the polynomial, but what we're interested in is where it is equal to 0, and it looks like it crosses at negative 4 and positive 4. I'll find one of those using a count 0 option. You should check the other also. So let's do second count option 2, and I'm going to look for the 0 that's to the left of the y-axis. I need to set a left bound. I can move the cursor, but that looks like it's going to take too long. So I'm going to set in as x, negative 5. A right bound, I'll set negative 3. And as a guess, I want to move a little to the left of negative 3. I'll use that value and push enter. The calculator's verified that one of the real solutions is negative 4. Again, you should go through that and verify that the other solution is positive 4. Let's go a little further with a different kind of example. Here it is. We've got a polynomial given in descending powers of x and factored form. What we're going to do is graph the polynomial either by hand or in the window suggested on a calculator, and then, using our graph, solve the equation and inequalities. Let's go ahead and graph this on a graphing calculator. So, on our calculator, we want to get rid of the previous function and put in x to the third power minus 3x squared, then minus 6x and plus 8. There's a number of different windows we can use. Let's set this one. Keep the x's at negative 10, 10, but set the y's to negative 15 and positive 15, and push graph. Here's a graph of the polynomial. Keep your calculator handy as we write down the solutions to the equation and inequalities. It looks like the graphing calculator crosses the x-axis, or is 0. I should have said the function, I said the calculator. The function crosses the x-axis at -2, +1, and 2, 3, +4. The solutions to the equation, and I've written it here in factored form, are x equal +4 from the first factor using the zero product property, x equal +1, and x equal -2. Those are supported by our graphing calculator graph. Now again, keep your calculator in hand, and we want to answer the question or find the values of x for which p of x, remember, is less than 0. That's our next piece of information. On a graphing calculator, that's where the polynomial is underneath the x-axis. The intervals for which this is true are from -∞ to -2, not including -2 since there's no equal to here, as well as from the x value +1, to +4. These two intervals are where the polynomial is underneath the x-axis, less than 0. Our third piece of information is we want to know where's the polynomial greater than 0. Again, with your calculator in hand, with looking at the graph is above the x-axis, bigger than 0, from -2 to +1, and from +4 to infinity on these two intervals of x's. Because there were two intervals as answers to parts B and C of the previous example, it's conventional to write a union symbol in between the two sets that satisfy the inequalities. Now I want you to try a problem. A polynomial is given in terms of descending powers of x in factored form. I want you to graph it either by hand or in the window suggested, solve the equation and inequalities given. Stop the tape and try this problem, and then restart it to check your work. Let's start by looking at a graph of this particular polynomial. I'm going to use a graphing calculator. We need to get rid of the previous one, and I'm going to enter the function -x to the 4th power minus 4x to the 3rd plus 3x squared plus 18x. If you graph this, you know we need to adjust the window a little bit. Here's a window that I would suggest you could use. Let's set x min to -5, x max to 5. Let's set y min to -30 and y max to 30, and look at the graph. Here's a graph of the polynomial. The first question we needed to answer is where's the polynomial 0? It's 0 at -3, 0, and +2. Keep that graph handy as we answer the questions. P of x is equal to 0 at x equals 0, at x equal -3, and at x equal +2. Notice that these are the things that we would get if we set the factors equal to 0. Now we want to answer the question, where is P of x greater than or equal to 0? Now we're ready to answer part B, which is to write the interval or intervals where P of x is greater than or equal to 0. Again, looking at your graph, the interval where the polynomial is above the x-axis is from 0 to 2. I've used brackets because of the equal to attached to the inequality. There's also one other point that satisfies this inequality, and that's the value x equals -3. At that particular x value, the polynomial is equal to 0. Part C says we want to list the interval or intervals where P of x is less than or equal to 0. p of x is less than or equal to 0 from, using a parentheses, not a bracket, negative infinity to 0, and then again from 2 to positive infinity, we do need to put the conventional union symbol between these two sets. Let's move on from this example to a particular theorem, and then we'll use it. The theorem is this. It's called the complex nth roots theorem. It says if n is a positive integer and k is a non-zero complex number, the equation x to the n equal k has exactly n complex roots. If the power on x is 2, there are 2 roots. If it's 4, there are 4 roots. If it's 3, there are 3 roots, is the connection. Let's do an example of this. What we want to do is find all n complex solutions of the following equation of the form x to the n equal k, and the equation is x to the 6th equal 1. That means we need to find 6 complex solutions. Here's our equation. Let's begin by using the zero product property. I'm going to subtract 1. Now I'm going to factor, treating this as if it's a difference of squares. It factors into x cubed minus 1, x cubed plus 1. Each of these factors more. The first is a difference of cubes. It factors into x minus 1, x squared plus x plus 1. The second is a sum of cubes. It factors into x plus 1, x squared minus x plus 1. I need to set all of these factors equal to 0. Let's begin with the binomials. This factor, set equal to 0, gives us the x value 1. This factor, set equal to 0, gives the x value negative 1. Those are 2 solutions. The other 2 are quadratics. To set them equal to 0, I'm going to use the quadratic formula. Starting with x squared plus x plus 1. Substituting into the quadratic formula, x is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1, all of that over 2 times 1. Simplifying, this is negative 1 plus or minus the square root of negative 3 over 2. Pull the negative out of the radical and use the symbol I. The solutions are negative 1 plus or minus I square roots of 3 over 2. The other quadratic is very similar. It was x squared minus x plus 1. Again, using the quadratic formula, I get negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 over 2 times 1. This simplifies in a similar way, 1 plus or minus the square root of negative 3 over 2. Again, we pull the negative out as an I. X is equal to 1 plus or minus I square roots of 3 over 2. We had a 6th degree equation. We need 6 solutions. The solutions are, remember our previous work, positive 1 and negative 1. Positive 1 and negative 1. This is actually 2 solutions, negative 1 plus I square roots of 3 over 2, negative 1 minus I square roots of 3 over 2. And in the same way, I have 1 plus I square roots of 3 over 2, and 1 minus I square roots of 3 over 2. 6 complex solutions. As a final topic in this section, what we want to do is work an application problem involving a higher degree polynomial. Here it is. What we're given is a rectangular piece of cardboard. That's 12 by 18. We're going to make it into a box with an open top by cutting squares out of the corners. What we're going to do is let x represent the length of each side of the square. We want to do a number of things. We want to give restrictions on x, describe the function v that is the volume, find the x for which the volume is a maximum, find the maximum volume, and find the x values where the volume is greater than 80. Well, we want to start with the restrictions on x and the volume. Let's do those two parts together. The volume of a box is found by multiplying the length, width, and height. In our particular case, if you look at this diagram, one side of the rectangular piece is 12. If we take two or cut squares out of the corners of length x, the dimension inside the box is 12 minus 2x. In a similar way, the dimension inside the box in the other direction is 18 minus 2x. And if we fold the sides up, the height of the box is x. Let's write that down. The volume is 12 minus 2x times 18 minus 2x times x. This is the volume in terms of x, which was part B of the problem. Part A said write the restrictions. Well, if one of the dimensions of the box, of the cardboard, is 12, we can't cut a piece out of either side or both sides of any size bigger than 6. So, and of course, we're not going to cut a negative piece out of each side. So the biggest thing that x can be is 6. The next question, part C of this problem, said, for what x value will the volume be a maximum, and what is this maximum? Let's use a graphing calculator to help answer this question. On our calculator, we want to put in the volume, 12 minus 2x, 18 minus 2x times x. We need to set a window. I'm going to choose 0 to 6, my restrictions on x. And then, planning ahead, I'm going to use 0 and 250 for my y values. Here's a graph. This is a piece of a polynomial function. The maximum volume occurs at the vertex, and the maximum point also. Using a calc maximum option, I'm going to set my left bound with my cursor and the right bound in a similar way. Let the calculator make a guess and run the volume program. The maximum occurs at x equal 2.35 and is the value 228. Let's write that down as part C. X equal 2.35, the maximum volume is the number 228.16, the maximum volume of the box. The final question that we were asked was, for what x values will the volume be greater than 80? Again, we can use our graphing calculator. As a second function, I'm going to put the function 80 and push graph. If I find those two x values, this one and this one, for any x in between those, the volume is greater than 80. I found them ahead of time. They are x equal 0.42 and x equal 5. As long as x is in between these two values, the volume is greater than 80. In this lesson, we looked at polynomial equations of degree greater than 2. We worked some examples finding all the complex roots using the zero product property. And we worked one application problem involving volume. Be sure to work many exercises from your textbook to practice this material.